Well, it's our great honor to have as a visitor Carsten Binnig from TU Darmstadt, professor there, and on the occasion of Madelon Hulsenbos PhD defense today, and you are in her committee. We are very glad that you wanted to give a talk, and about a very completely non-fashionable topic. So take it away.
Thanks a lot for that. We had the discussion before in Peter's office in the 2000s, when I was kind of still at the very beginning even of thinking about a PhD. XML was the hot topic at that time, and you couldn't get around XML. And everybody was working on XML. Maybe people here don't even know it anymore. So you know what happened. Now we are in LLMs, so only one letter changed and a bit of different orders. And but let's hope that this is a bit more a trend that will be there in 20 years from now on. And let's see, not speculating, but Peter said it's most likely to be more successful than XML, but this is not a high bar. So. Good. So with that, let me introduce quickly. So what I'm talking about. The title is LLM-augmented database systems, and this is a work jointly with some other senior researchers and PhDs at TU Darmstadt and some external collaborators that are not on the slide. So everything I'm talking about today is also due to the effect that I have a great team behind the work that I'm showing here. So if you look at databases and what database has been successful in. Quickly see if I have focus. Yeah, databases have been a success story, right? In the last 40 years. And databases, what they offer to users is a very simple model. So you can store tables in databases and you can query them with a declarative query language. And what we've been focusing in as database researchers mainly in the last 40 years was in performance. So if the data scales, we want to efficiently be able to get answers back on the data sets we have in databases. And our main really core focus has been on this issue of pushing for performance forward. And what this feels like at the end is that what we have today is more like a, way, clicker doesn't work, sorry for that. That databases look like an overtuned vintage car, right? It still has the look and feel of an old car. You need to do everything kind of yourself. You can only have tables and SQL as a query language. So using it there's nothing like luxury in there, right? It's still the old car, which really drives fast, but there's not much more to it. And so this is there has been a reason why this led to the success, but I'm arguing in this talk that we should go beyond that, what databases offered since the last 40 years, and we should look beyond that. But what has happened in the last few years is with the rise of ML, people didn't really look into changing that, what databases can offer, but they fix it. Yeah. They try to improve performance by using ML. So the most recent kit on the stage and the database landscape is ML, but it's still used for performance tuning mainly. And the trend that you might have already, all here in the room have heard about is learned database components. And here the idea is that you replace one of the performance critical database components, like an index, like the optimizer, a scheduler with ML model, such that it can provide higher performance for end user queries. And while this is clearly, as I said, interesting and important, but this doesn't really change the vintage car into a more modern car. And what I'm looking into with my team at the moment, now I'm completely confused, is the direction of LLM-augmented database. And here the idea is, instead of using ML to make databases faster, the general idea is, can we use ML and we use LLM as one of the instantiations of ML models to make databases smarter, so to modernize databases, thinking about what of the basic assumptions in databases can we relieve by using LLMs when they are used jointly together with database technology. And to walk you a bit, I want to walk you in this talk through some ideas that we had in the group. And there are many more ideas where you can clearly go beyond what I'm showing today, but what this means for databases and how LLMs can help to modernize the old picture of database systems. Okay, it's working. I was just confused. I clicked, it was 1 second later here, but it works. Good. So our vision of an LLM-augmented database system, where we started off, is the question, can we give database a bit more modern look and feel? And modern look and feel means today people don't want to just query tables, but they clearly want to go in querying in different modalities. And here I have an example of a medical data set where you, for example, have tables along with text descriptions or patient metadata, doctoral descriptions which say something about the patient, for example, the diagnosis, as well as images which might be some kind of medical scans that give additional information about patients. And this is clearly also what modern machine learning world gives us. If you look at what LLMs are doing today, they allow you to input various kinds of modalities and then kind of ask questions about what is in these modalities. Same on the other side, what modern LLMs give us is natural language interfaces, right? Instead of using SQL, so Peter just said it, or when I write a query, I always have to remember the concrete syntax of SQL. So what people actually want is they don't want to remember concrete syntax of SQL, but they want to query data more naturally. And so our vision of a LLM-augmented database is, can't we just go in this direction, how everybody today kind of works with data? So natural language interfaces, this is something that everybody knows from LLMs, and multimodal data, but give the users kind of the same performance guarantees that databases have today. So let's move a bit further. So this is the vision, and clearly you could say, Carsten, you just said LLMs solve this, right? So why do you need to put databases in the picture? And when I say LLM solve this, so querying multimodal data with natural language interfaces, I mean that actually LLMs are used for question answering by using retrieval augmented generation today. This is the state of the art today on how to process and answer queries on multimodal data sets. And what this means is what you actually do, you combine a large language model with a vector database, and how the procedure for retrieval augmented generation works, for those who have not looked into that, is that you have your user queries, so what is the average duration of stays of COVID patients. You get the same data sets that you had before, tables, patients, tables, images, text stored in a vector database. You use your user query as a query string to retrieve the right information, because there might be much more in your database than just the relevant information you need. So you retrieve based on the query string what you need. You feed the query and the relevant data into your LLM. And then the generative nature of the LLM, you hope that with all this context you put in the prompt, you'll get the right answer, right? So you will get most likely an answer if you ask a question like this, which so is the average duration. You will get some kind of a time duration. But at the end, you even don't know if this is the answer that you wanted to get, and if this answer is correct at the end. Good. So LLMs seem to solve it. But as I already said, there are many issues with LLMs. And hallucination is just one of them that I mentioned before, and everybody knows it. But if you use LLM for question answering, there are many, many more kind of problems if you really want to do this at the scale where databases operate today. So, and one kind of problem is that there are issues regarding the input data, right? LLMs faced for a long time input size limitations. So what you could put in a prompt in terms of length is really limited, or was limited. Current LLMs have support larger prompt context length as input, but still with growing prompts, people have shown that LLM's accuracy is kind of getting worse, because something that is in the middle of the prompt, meaning something that you put somewhere in the middle of your data set, will not be as visible to the LLM as something that is at the beginning, at the end, which is bad for a database if you just ignore the facts in the middle. The second one is, while they are multimodal, they are still hard to extend towards new modalities. What they typically do is they need to train some form of adapters that map everything into textual representations, and then you can support this new modality. And so therefore, you need, again, new training data, et cetera, pp. Clearly, there are some ways of doing this efficiently as well, but it's still a labor-intensive process to add a modality to a language model. And another, I'm really confused by this. I should have looked at that machine. The second problem is with query processing, I said it before, there's hallucination of results. So you get an answer, even maybe if the fact is not in your data set, it's black box. At the end, you cannot look at it, right? So can't argue, is this 11.2 weeks? Is this right? There are some forms, Paul is shaking his head, but at the end, so you get some results and there's no real explanation to it why it happened. And LLMs are quite slow, even on small data. So you have to put it in the input context. If it's getting longer, it's getting really, really slow. And in terms of databases that learn to process petabytes in short time, this is not comparable at all. And the question is, so can we kind of tackle these issues with an idea where we put database technology first, right? So the idea is, don't start with LLM as a query processor, but use whatever database has invented in the last 40 years to give high performance query answers and query processing, and augment it with LLMs such that we get still multimodal question answering, but with the performance guarantees of a database system, or with higher performance and better scalability. And so here's the first. Somebody's asking a question, or somebody's unmuted.
Yeah, maybe make sure that everybody's muted.
Good. So the idea here of how we enable this was published in a recent vision paper at CIDR this year. It's a system called Cesura, which we called an LLM-augmented database system, where we use LLMs not for actually executing queries, but just for doing the query planning task and a bit of query execution. So what does it mean? And how are we different from the LLM-based retrieval augmented generation? So the basic idea is that if a user query comes in, so here we have another data set, just maybe let me set the stage, for an artwork data set where we have a table metadata about artwork, and per artwork, we also have the image of the artwork itself. And users might ask questions, so give me the number of paintings depicting Madonna and child for each century, right? So you see this histogram plot here, and you see in the 13th century, Madonna and child was kind of a really important theme in artwork. So the question is now, if such a query comes in, how do we do that? You can do this with retrieval augmented generation. Again, feed this in the LLM and hope that it gives you the right answer. What we do is that we take the user query and we actually translate it into query plan. So something that databases do, right? Because we want to optimize the query plan. We want to reorder operations. We want to reason about query cost. And the query plan itself is executed outside the LLM, while for the translation procedure itself, we use the LLM. So reasoning about how to stitch together the data sources and how to process it. One extension is that the multimodal query plan does not only contain relational operators, but in order to read images and process images or text, we need other operators. And this is what we call multimodal operators, and therefore we translate a query into multimodal query plans. And here's the basic idea. So the query is coming in, the query plan looks like in a database query plan. For this example, the query planner, which is based on LLM, might decide that for the table, you can simply use a scan if you don't have an index. For images, you should use something like an operator that does kind of visual QA, right? For each image, you need to decide if Madonna and child is in it. So this is just a logical description, not just physical saying I'm doing it with this kind of code or feeding it in an LLM. Just tells us what to do. We want to do visual QA on the images. And then clearly you want to join these two outputs. So for the images where the Madonna and child are shown, you want to join it with the metadata. Then you want to go do an aggregation count by century. And then at the end, you want to get the result, which is maybe also a non-relational operator because we will produce multimodal output as well here abroad. So the output does not necessarily also need to be a table, but it could be anything. Could be text, could be images, could be a table. So clearly, this is a nice vision, right? So the question is now, how do we get from the user query down to such a query plan, which is at the core of what we are doing? And maybe before I go into that, so the kind of the good sides of this approach are, since we execute outside an LLM, we can be more scalable. We can build on algorithms that databases have used, for example, for joining. We don't ask the LLM to join data sets, right? It's there. You can use a hash join. You can use a hash aggregate that is parallelized that uses modern hardware. Clearly, for multimodal operators, the question is different. How do we get efficient multimodal operators but this is also something I'm covering in the second part of it. The second nice thing is users can then actually inspect this query plan, right? So it's not just, oh, there's 42 coming out of or 11.2 weeks out of as an answer out of the model, but you can look at what actually the process was to produce a result. And really, if you just think about that as a logical plan, you can extend this by new modalities. You have maybe to instruct the LLM that you use for query planning that there's a different modality and a different data source. But at the end, you could then add just a text collection or another modality to this engine. Good. So how are we doing this? So this is maybe now the core question here. And you could kind of think of, yeah, let's put in the natural language question, and the output is a query plan, right? So a query plan that can be at the end even be executed. But this is a long way from input to output, right? And you miss opportunities. You miss opportunities potentially for optimization. If you directly go from input query to code, but LLMs are used for also code generation, this is maybe too much. So the question is, how do we translate them and enable the kind of optimizations that databases do today? And I will walk you now through this translation procedure that we apply in Cesura. So the basic idea is that we feed in like the metadata about the data sources and what we call operator descriptions. So what can you do with the data, right? So logical operators, a collection of tools LLM can use into the LLM, which is known. So people who heard about tool format, this is a similar idea. We tell it what tools are there, what data sources are there, and then ask the LLM to come up with a stepwise logical procedure on how to process data. And this stepwise procedure is not yet something executable. It's more like a logical query plan in databases. First do that, second do that, third do that. And for the options, what we do in each plan, this is restricted by the tools we give, right? So you might want to have at the beginning something where you scan the table and you immediately apply a transformation function from years to century. Then you do the selection of paintings with a visual QA model to find out images where you have Madonna and child, and then you join the images with metadata rows. So this would be a textual output that comes out of an LLM, step 1, step 2, step 3. And this is what we then translate into a query plan. It's already kind of a stepwise procedure that you can put afterwards in a graph representation on how to execute the query. And herefore we use prompting, right? So we prompt the LLM with the metadata and instruct it to create a plan that tells us in a stepwise manner how to proceed queries. Afterwards, what we then do is, this is only a logical plan. It does not yet tell us how to execute it. We then ask the LLM to do a mapping phase by prompting. So we select for each of the logical steps a real physical operator that can execute it, right? So given a CSV file, how should I extract the years from a table which has essentially from a table that has years? You can use Python data frames, which applies a bit of a UDF function to the table, for example. For selecting paintings from images, you can do visual QA, and for joining, you can then, with both output data frames, you can use a SQL if you store it in a database, or you can use, again, some data frames for that. And what we actually do then in that step is, so when you go from here to the right, we generate code for each step so that it can be executed. So that's a bit on what we are doing. The magic is again clearly on how we prompt things and what the prompts look like. But this is, so I'm not going to detail here, but I think the intuition is clear. You have, everybody has maybe here worked with prompting. You have to kind of tell the LLM exactly what to do, what are the options that can be used. The nice thing about this approach now is that it allows us optimizations in every phase. Right? So here in this phase, you can think about, for example, if you have joins of multiple data sources of join ordering. So if I join a table with a textual source with an image source, you can argue about joining, for example, text with a table is better because it's highly selective, and then we only need to look at a few images at the end. But you can also apply optimizations here because you can reason about if, for example, if you use a certain operation, what should I use? right? Think of, for example, a text collection instead of image collection. You could use textual QA, right, to find out if something is in a text, but you could use simply a regex for it if the text is maybe more structured. And reasoning about what physical actually implementation to use is something that you can do also in the second step. As I said, there's much more to that. I'm not going into detail in that. The question is, how do the prompts look like? There are examples in the paper for that. Clearly, there needs to be error recovery because we don't get the plan correctly, correct plan in the first step. For example, we often have wrong logical plans because the LLM thinks there might be something in the table that it can extract, but it actually should extract it from the images. And therefore, we have error correction procedure, and our current error correction procedure is so we are at the starting point of that. But what we actually do is we feed the error into the LLM, say your last plan was not really good. This is the error we got. Give me a new plan. And for a new plan might be just here, give me a new step of procedures. So the first step worked, but restart from the second step. And this has shown actually to be very effective that they self-correct the plans. Good. There's more to the error recovery phase, but let me come to maybe some initial results. How good does this work? Clearly, the starting point here is we don't have any data sets. Clearly, there's a lot of QA, work out there, but usually this is very, very simple. Doing question answering with language models, many of them are kind of extractive. Questions that try to extract something from a single source. Sometimes they are spanning two sources, but it's still extraction. It's not really higher level complex queries like aggregations and so on. So we've built our own first data benchmark for that, which contains two data sets, one that mixes images and tables and one that mixes images and text to have different modalities and different data sets. So one is this artwork data set that I've showed before, and the second one is a data set that comes from the sports domain that has team information and reports about the sports events. So who scored how many points, so which team scored how many points. And for that, we created a list of 48 queries that are different in complexity. Some involve two modalities, some only involve one modality, and also in the way what queries are in there, if they involve aggregations or not, is different. So in our experiments, we use different language models. I'm now showing the GPT-4 results first, and then I show a bit how the other language models, if you use them as query planners, how well they are. I'll go over the overview, over the complete results, and then I drill down a bit. So what we see here for the first overall view is that from these 48 queries, how well could the language model produce a correct plan? And correctness means that now correct logical or physical plan. So correct logical means we have the right steps, right? Correct physical means we generated the right code. And this is with error correction enabled. So it doesn't mean that we get the right plan from the beginning, but at the end, after self-correction, the LLM might have found the right plan, or has found the right plan if there's 100%. So for the artwork data set, which has images and the table, and this is actually a bit more complicated than shown here. You see it in a minute. We get 100% accuracy with GPT-4. With GPT-3, we'll see it in a minute. We were much, much lower in accuracy. For the RotoWire data set, so baseball data set with text and tables, we are a bit lower. So the overall approach seems to be really, really interesting and work really well. The second kind of part of the results that I want to show is a bit the breakdown across the two data sets. If the queries involve a single or multiple modalities, clearly single modality queries are better, easier to understand for the model than multiple modalities. And also here, the question is, what is the result? Is it a single value, so 42? Is it a table or plot? And with a higher complexity, the accuracy also goes a bit down. So if we produce a table compared to single value, the results are not as accurate because sometimes the model even doesn't generate an operator that gives us the right table. And I guess that's a bit from the overall view. Maybe another interesting comparison is we started this work when GPT-4 was not out. So we played around with the GPT-3.5 and older other models, and you kind of see already the steep or the high difference between 3.5 in compiling correct plans, which was around 50–60% compared to the GPT-4 results that we got. Good. And interrupt me if you have any questions. Yes.
So just a quick clarification. Why is it on the overall 100% and you have single modality? Is that,
this is across two data sets.
Got the
It is cross rotowire and Barbara. This is aggregated across the two data sets, not by data set. Yes.
Have you tried answering the query directly with GPT-4?
So this is so the retrieval augmented generation kind of approach that I mentioned, or do you have something else in mind? So we tried out retrieval augmented generation recently because the multimodal capabilities of the language models came in with GPT-4 Turbo. When we wrote the paper, that was not yet there. So no, for the particular experiments, we don't have it. Yes.
So when there is an error in logical plan, you have to manually find the error, and then
no, it's not manually. Right? So it's you get a logical plan, and you might realize. Typically, so when we execute the physical, so I didn't talk about. So we compile the logical plan, and then we compile the physical plan one by one. We don't compile the physical plan all at once, but for one operator, we decide how to execute it. We might realize that this operator is not executable, and this gives us error message. Column A was not in CSV file, and we feed this error message into the language model and say, kind of give us try to fix it by either giving us a new step, a new logical plan, or correct the physical. We don't know actually where the problem is, right? But we feed all the error messages in the LLM and try to recap, reproduce a new better plan. We try to do that manually, not manually, but in a procedure first, try to fix it on the physical level. If this doesn't work, we do it on the logical level. So we step back to the logical plan. But this is still at the very beginning. So we tried this out, and for many of the errors, this worked well. But I think there's much more to do for error correction.
So on the physical level, it seems that what you expect to get out of the operators are some kind of data frames, or is this more general?
So once, so our model at the moment, I didn't talk about that. Once a multimodal data source is produced, so it's processed, the output is a data frame, like some kind of a table.
Do you have an expected kind of correct metadata signature, like at least a data frame with these and these? I expect a data frame with these and these columns in it. So when you don't get that, you know that it's wrong.
So the logical
and how often is it wrong? And can you then correct that?
So we have also breakdowns on what types of errors the language model makes. I think I'm not having them in the slide deck. They are in the paper. So sometimes, the errors might be complete. So it might even assume that so some information is in a data source and it is not. Sometimes it generates the wrong output, and this is a bit the breakdown that we've shown.
Yeah, but I mean, it's kind of natural that you use the language model to correct a query if you got an error message.
Yes.
But you could take it a step further, and you could maybe have, well, at least like these. You have them apparently, these signatures of the data frames that you expect. So if you don't get that, then there is something wrong. You can ask it to. But you could even take it more further and saying, okay, I have some constraints or expectations on the contents of these data frames. And if I see that they are not met, I will ask the model to,
we are not,
to try.
This is why I say error correction. So this was there's a lot to do. So this is this is a vision paper at CIDR. I guess there are many more research questions than answers that I could give to you. But yeah, so I didn't mention it. The internal processing kind of scheme is that internally everything is still a table, right? So after visual QA, the output is a data frame that then can be joined with another data frame, right? And if you have a text data source, we would turn it in a tabular data structure that can be further processed. And at the end, it could then be turned again in a plot, for example. Yes.
How does the joining look like? Because you have images there, how do you?
So the output of a visual QA operator is the data frame, right? So saying for this artwork, is Madonna and child depicted, yes or no, right? So it's the second column is a binary column.
But
So
then-
the input is still images, right? Input.
Yeah, but how do you join it with the metadata then? Because you have an image and you want
So-
to expect something that identifies the image and.
Good question. So, let me go back to because I left out.
Sorry, meta point. You have been waving your hands a bit, and the camera has gotten distracted. Maybe you can wave it again, so it starts following you again. Yeah, like.
Like that, this is on the recording.
Wait.
Hey, everybody.
Wow, then we should give up.
Okay, it doesn't want to.
No, it should flash. Okay, leave it. But it will not move anymore. It's okay.
Okay, I try to
Continue.
stay here.
Sorry for the interruption.
No worries. So what we have actually, so is also for the image collection, you see kind of here is a image path in the table, right? So it's kind of a linked data set. It's not completely unclean. And you have some weird image collection from some data source and the CSV. So the assumption here is that the data set is already kind of like a curated data set. You can still ask the question, what if this is not the case? If you start with, I don't have this information, I need to kind of find the join partners, but this is maybe where LLMs are also good.
Yeah.
We assume that this information is there for now, but clearly interesting question. Can we get rid of data curation by LLMs as well? And there's a lot of work on that. Bella? Good. Okay, let me maybe move further. So I'll come to the performance angle. I saw a query, so question here in a bit. And people are looking at what is this? So here, just another kind of result from our paper, and this is more like an anecdote, and don't look at it in detail. This is just telling you or showing an example on the other data set on how an actual plan looked like for a certain query. And I want to use this to motivate a bit, how do we get the high performance in multimodal query processing? So what you see here is the Retrieval data set with multiple tables, so teams, team to game table, and the game reports. And with the game reports, one textual data source is linked, right? So you have a team, you know which games the team was playing and the game reports tell how the game went. So who scored how many points in the game. And the user asked the query for every team, what is the highest number of points they scored in the game, right? So we want to know if for all the games, the highest score that the Heat team was scoring was 98 points. And this is the plan that Cesura came up with. So in a nutshell, what it does, it joins the tables together with SQL joins, then it kind of uses the output to do in the middle a textual QA where we take the team names that come from, or the game IDs that come from here and the team names to create a textual QA operator. And this is one that I'd like to look into next, where we kind of asked for each game and team, how many points did that team score in this game, right? And we expect the integer column coming out. This is a bit so how our internal interface looks like. This would be the description of the metadata we expect, right? So if you look at this operator, this turns the textual inputs, right? So per text, it creates output row at the end. I didn't show that here, where we have the game with the team and the points the team scored. Right? At the end, you have a table with 3 columns. But important is here that this operator turns the text plus the additional data coming from the SQL join into a structured output. Yeah.
How do you discover the join columns? Is something that the
That's
LLM
given.
tells you?
No, that's given.
Given.
So this is given also in the metadata. You kind of see that it's a curated data set, right? So here the link would be for every game report, you know which text file is used for.
That's okay. The camera woke up again.
Well, oh, well, okay, good. So where I want to get now, so this is a real plan we produced, but we still have an issue, right? And the issue is the textual QA. I told you before we can use all these nice operators for SQL joins, which are fast from databases, but the textual QA operator, if you use, for example, an LLM for that to do that, will still be slow, right? So if the procedure that we actually need to do in here, it's a bit shown more with a zoomed in version of what we do here. So the left part from the plan gives us this table, right? Game reports and team names. The right part, the input source, gives us per game file, right? Per game, we have the textual report. And now we want to know how many points did a team, so Spurs, for example, it should be Spurs, kind of score in a game, which is kind of where the information is in this report. And the output is a table like this. In game 1, Spurs scored 190 points, and Lakers in the same game scored 122 points, right? And for this visual QA, you could feed this question plus this text in an LLM and get this table or the answer out, right? But this will be terribly slow, right? And this will slow down our query execution. And the question is, can we do better? And this is now a second work that I'd like to zoom into that we've done. Can we have efficient multimodal operators? And just to give you an idea of what inefficient means is, if you do this for one of our data sets, which has 1,000 texts, so the RotoWire data set comes with 1,000 game reports. If you turn this in a table with 1,000 rows, which lists the team name and the points the team scored in this game, with GPT-4, you will wait 2.5 hours to get this table.
And you will pay.
And you pay. That's another argument against it. The second, clearly, if you go with smaller models, and just as an example, if you use GPT-3.5, I guess it was, you're faster, but you massively lose in accuracy here in turning the text into tables. The question is, can we get into something acceptable? And this is what we've done with this work, where we have a language model that is kind of tailored for text-to-table scenarios, that does this kind of transformation of tables into text, from text into tables for the same data set in 10 seconds. Yes.
I don't understand. So
yeah, let's just stop me.
When you say it takes 2.5 hours to transform the text, this is like take one text at a time and prompt the model. Okay.
You could still batch, but this is since it's typically this is just a longer context then, so you gain not much by batching. Thanks. There are still tricks you can play. This was the naive way, right? 1,000 text means we query or prompt the LLM 1,000 times and extract the structured data for the 1,000 reports. Right? One text is one line in a table, kind of. Good. So what we've done with Elite is an idea. Can we use kind of a really much smaller language model that is really focusing on the task of text to table and pre-train it such that it works hopefully out of the box also on unseen tables, right? That you can use it if you pre-trained it on large enough data, right? That you can use it on a tabular data and a textual corpus that you haven't seen before. And what we've done here, just in a nutshell, so first of all, again, question is, how do you train this, right? You need structured and unstructured information. We've been building a parallel corpus of texts and tables, which is also released. It's not yet released because the paper is not yet published. It's submitted. We will release this parallel text table corpus, and we pre-trained this table extraction model from text. And overall, this has only 100 million parameters. And we also have a dedicated model architecture for that I'm hopefully showing in a minute, but I'm not sure how I'm in time. Just stop me when I'm too slow. Good. And the idea here is that we have a particular pre-training procedure. And what we actually do is align text with tables, right? So we have alignments that align the column values all from the same values with the textual representation, where we do row alignments, meaning multiple rows, how they align with the text. We have a pre-training procedure for that. And one that was particularly important is duplicate removal, because you don't want to extract things twice because they are often mentioned in text redundantly, and you don't want to have redundancies sometimes in your output, right? If the game scores are mentioned twice, you don't want to extract them twice. You want to only have them one time in your result, and you want to be able to detect duplicates and reliably remove them. So how, and as I said, it should be zero-shot or used with fine-tuning if you have a text corpus that you turn in table for unseen domain. So how does the model look like? Just a quick overview. This is, again, a plot that don't focus on every detail. We have an encoder-decoder architecture. We map the textual and kind of table information into one single representation space and train this. And the idea here is so that the input is the text we want to extract it, and the kind of table description is handed in as a structured list of query attributes, like using just a normal textual representation. And what we've done here, the important part is that so these pre-training tasks that I mentioned before are applied on this model architecture, and we have several decoders that help us, for example, for doing extracting tasks on text, so turning the text into tables. So for example, we have one called of span detect decoder that tells us if data in the text is either the beginning, inside, or outside of a text span. So which allows us then to do extractions on text that we handed into the model. So the idea is encoder, decoder with different heads for the different tasks we use for table extraction. So there would be duplicate detection head, for example. Good. In interest of time, let me skip over that section and go to the results for that part. So this is, again, so now the question on how much does this give us on performance compared to accuracy we get for the text-to-table task. And here we compared, again, different existing language models like GPT-3.5 for a fine-tuned 3.5 for the text-to-table task, Llama model not fine-tuned, and a supervised learning model for text-to-table, as well as our own model, right, Elite. And what you see here is the accuracy versus runtime, and the higher the better, higher is lower runtime. And what you see here is that, first of all, so from accuracy, clearly there are models that are competitive. GPT-4 is not much worse than our model. It's not our claim we beat these high capacity models, right? And this is also seen a bit by the distribution of accuracies, which you see up here. So sometimes in some areas they are even better, but so they are sometimes better, right, in the really high accuracy regimes, but we are not as far, right, or spread across the accuracies that much. So we very much give accuracy, high accuracy for all the queries and data sets. So one dot I mentioned that is one table extraction, sorry. So these are multiple experiments with multiple tables being extracted from the same text collection.
You have a dollar cost comparison?
No, not. Well, yeah, we have it, but not here in this plot. We paid for it. And my student asked me for the paper, Carsten, if I do fine-tune, if I do in-context learning GPT-4, where I really put examples in, this will get much more expensive. So one dot Carsten costs you $80. I said, okay, let's think about what we do. Good, okay. So this is where we are. And importantly, the kind of runtime for getting a table, you see we are in the orders of 10 to 100 seconds versus GPT-4 models, which are in the orders of hours, right? So we, in the best case, we speed up by a factor 1,000, but clearly the answer is somewhere in between. Good. Let me finish maybe, and then I'm happy to also take more questions. The question is now, is this everything we can do with LLMs for databases? And clearly there's much more to be done. And I just want to give one example of where I think LLMs can also help. There are many more, I think, ways of using LLMs to making databases smarter. And one direction that we also looked at is the question, so databases are great, but they allow only closed world querying, meaning you can only query the data you have. So for example, you have a movie database, so you can only answer questions that are in the database. So revenues for movies or per genre, but not per actor, right? Because you don't have the actor information if this is your database, clearly. So the question is, can we kind of relieve this assumption also by using LLMs? And here, the idea is if we can kind of use the common sense knowledge that LLMs have and use that to augment database tabular data with information that a user wants to have, but that is not stored in a database system. For example, if the user asked here the revenue per for a certain type of movie where actor was kind of acting in the movie, you would not be able to do that. But if you ask the LLM, so which actors are in Avatar, the LLM will most likely give you this list of actors in Avatar. So what you can do with LLMs is augment the database here that you have with movies, and for example, construct a virtual actors table that is extracted from the LLM itself and link it to your database, right? So you could then join it and kind of see these are the actors that played in Avatar. There's another list for Avatar 2, which would be more kind of rows in this table. And then once you have this, you can use SQL again to get the answer. The question is clearly, so how reliable is this? And when do you know even that your table finished, right? So if you want to get a list of all actors, when do you stop prompting the LLM to ask for more actors? But so here we had a workshop paper last year, and this is also work that is just showing that it's possible. What we've done in the work, we used the prompting approach. There was nothing with fine-tuning the LLM, but we kind of asked the LLM, given certain information, can you complete the information we need for answering the query? It could be just another column in the same table or a completely different table. Here's an example where we augmented a table with a new column. And what we do is just prompt the LLM kind of with a structure of the table and kind of say, continue, so generate more for this table, and we prompt it with the attribute we wanted to have. And the question is clearly how to construct prompts. There are different alternatives and what metadata to use for prompting. So should we use visual or textual QA? So kind of what is the director of a movie, like a natural language question that we use for prompting, or should we use more this structured representation as a prompt? And many more questions. And this is a bit what we've shown in the evaluation here. Do we give kind of full rows serialized into the prompt? Should we give example values? All the things that people are doing today, right? So prompt engineering. And what you see here is, for the two data sets we had in the initial paper with cities and movies, it kind of works, right? We get common sense knowledge out. And this is a bit the difference on how well different prompts work. Interestingly, structured prompts work better than natural language prompts. Natural language prompt is, what is the director of movie of Avatar, right? And asking it with a natural language question worked worse than the structured prompt. Here is a structured row completed by a director. What is interesting, again, is here, for example, for movies, it's clear we've seen old movies that are not maybe as common sense knowledge as more recent movies. The information got less accurate. And I think going into and extracting information from LLMs and making use kind of implicit information stored in an LLM database, there's a lot more to be done. This is just a bit more of the breakdown of our prompts. If we kind of add some more row information, full rows versus partial rows, examples and so on, but this is, I guess, now for to wrap up, not that important. Good. So what I've shown is the work in our lab on LLM-augmented databases. I think if we look at the picture, what we've actually done is we went through the different database components and thought about where can LLMs help to really build smarter, more modern database system. On the query planning level, right? We had the Cesura work where we used LLMs for coming up with a query plan for reasoning about natural language queries and then compiling a query plan that can be executed. But we used also LLMs for query execution, which was the elite work for table extraction. They are good, but here the problem is clearly performance. And on the storage level, you can also think about many things, but one work we've done on the storage level is OmnitionDB, right? Using LLMs as an additional data source in a database where you can extract tables out from the implicitly stored knowledge. And I guess if you think about like component and LLM, so where can it help? This will just open up a much larger landscape of things. People are working now on kind of producing more error-friendly log messages, which would be another way of the user front end. Compiling SQL queries is maybe an example on the query planning level. And I think if you use this framework of database component plus LLM, you'll find a lot of interesting directions that you could work on. And with that, I hope that I'm I'm well in time and we have a few minutes for questions.